First derivative test. Let's do another one of those. 33. I kind of explained it briefly a minute ago. First derivative test. And we also want to test for concavity in a moment. So number 30, what did I say? 3? 33. X times the root of 9 minus x squared. Am I going too fast? Good. On the interval -3 to 3. Now, that restriction is not because we want to apply the extreme value theorem necessarily, it's just because that's where this function is actually defined. The function only exists from -3 to 3 because of the 9 minus x squared inside the radical. Okay? Just to have a sense of the function. They're not trying to get you to apply the extreme value theorem necessarily. Matter of fact, the question says, first derivative test. And part A is locate the critical points. So again, first thing is usually find critical values. Okay? Find, so I'm going to use CV, right? Find critical values. First derivative, set equal to 0, and find out where it's undefined. It's product rule. So first times the derivative of the second, d dx. We had something very similar to this just a minute ago. I'll write the symbols anyway. 9 minus x squared, we'll do it in one moment. Plus the second times the derivative of the first, d dx of x. All right, there's our product rule in notation. So now if we complete it, we'll have x times, again, the 1/2 comes down, so we have 1/2 root 9 minus x squared. I can't use that anymore though, can I? To the negative 1/2 times negative 2x. Again, very similar to the last one we had. There's a bracket there. Parentheses. Pow. Plus, the derivative of x is just x, so we just have plus a root 9 minus x squared. And since I have a negative 1/2 power over here, I'll write this as a 1/2 power here. Are we okay so far? First derivative.
Wait, why is it parentheses?
Where?
Oh, okay, because it's negative 1/2.
This one?
Yeah.
Yeah. I can't use the jagged
Yeah.
symbol anymore. Yeah. I've never seen it. I even feel like a little -2 out here for the index. Maybe. I don't know. Never seen it. All right. We need to set this equal to 0 and find out where it's undefined. We need to do both. So the first thing we should do is simplify it algebraically as much as possible before you put an equal sign on there. So to simplify it, what are you going to do? Factor. What factors do they have in common? Negative 1/2, right? The lowest power. 9 minus x squared is negative 1/2. So I'm going to factor off 9 minus x squared to the negative 1/2, and then we'll leave us with, again, 2 and the 2 here cancel. I've got a negative x and an x here. So negative x squared. When I factor this from here, it's going to increase this by the 1/2, right? I subtract off that power. Subtracting off negative 1/2 means adding a half. So I get plus 9 minus x squared to the first. So this time the squares do not cancel, right? The reason they canceled last time is there's a quotient rule and there's a negative here instead of a plus. This time they're going to combine and make a negative 2x squared. All right, so this is our expression, and we're going to simplify it one step further. We're going to remove the negative exponent. We're going to push the 9 minus x squared down to the bottom. So we finally have negative x squared minus x squared is negative 2x squared. So we have negative 2x squared plus 9 in the numerator, and that's really the denominator. 9 minus x squared to the 1/2. Now, we want to know where it's undefined, which we do want to know. We're going to set the bottom equal to 0. Agreed?
Where did you get negative 2x squared from?
These two guys together. Because the parentheses are just carryover from this expression. They're not really doing anything in terms of operation there. So it's just
2?
Yeah, there's 2 of them. Negative x squared makes negative 2x squared.
Oh, okay. I thought, okay.
Parentheses are not doing anything
Right.
except containing this for no apparent reason down here. They were useful up here for that power, but now they don't have that power anymore.
Okay.
They're not doing anything. To know where this is undefined, we set bottom to 0. that will tell us where a derivative is undefined, right? F prime undefined when this is 0. And if that is 0, that tells us where f prime is equal to 0. Okay? Which are the two things we need to worry about for critical values. Where is the derivative undefined? Where is the derivative 0? Okay. Let's do the numerator first. The bottom you guys already have in your head, right? What's the bottom? Negative 3 and 3. Now, are negative 3 and 3 important in this case? It could be, because it's defined for the original function, right? Okay. So we have to include them as
what does
critical
the
values.
top like mean?
What top? Where?
Like, if we set the top equal to 0,
That's where the derivative would be equal to 0, which means it's where the original function would pass through a horizontal tangent, right? It would have a horizontal slope right there. So that could be a max, or it could be a min, maybe. Or it could be nothing. We don't know. We need to find them. So negative 2x squared plus 9 equal to 0 implies that x equals what? Square root of 3 over 2?
2
Square root of
9 over 2.
Is that right?
Yeah.
Something like that.
Do we have to rationalize the denominator?
We're supposed to. I'm not a big fan, but since you insist, Raja, you know, whatever you want, man, you know, that's fine. And the bottom, you guys told me that 9 minus x squared, the root of 9 minus x squared equal to 0 yields x equals plus or minus 3. So now we have 4 critical values. So critical values are plus or minus 3 root 2 on 2 and plus or minus 3. We have 4 of them this time. Okay? All right, that was the first part of the problem. Part A, we found the critical values. That is, we've found all possible locations of maxes and mins. Part B, use the first derivative test to locate the local maximum and minimum values. B. What did you say, Rosas? I couldn't hear you.
Doesn't that mean you have to plug in all those numbers back into the original?
Okay, so that was the extreme value theorem. And that was finding absolute max and mins. So that was specific to the 4.1, the absolute the extreme value theorem. Here, you're going to use the first derivative test. So the first derivative test is when you put these on a number line and check the intervals. That's what we're going to do. So use first derivative test to find, it says, to find all local extrema. It does not say absolute yet. It says all local extrema. So, Lee, we're trying to find local extrema. So what about this negative 3 and positive 3 business? Do I care about them for local extrema?
No.
Why not?
It's got no area left or right.
Right. There's no function to the left of negative 3. And local extrema require open intervals around their critical values. There's no open interval for this function around negative 3 or positive 3 because those are the endpoints of the entire function. There's nothing to the right of 3, there's nothing to the left of negative 3. So they are not included